Hi everyone, thanks for your interest in this topic. In this video, I will talk about this paper, Characterizing Accuracy-Aware Resilience of GPGPU Applications. In this work, we aim to strike the balance between the performance and resilience overhead. Towards this goal, we propose the concept of accuracy-aware resilience. Basically, we offer users the flexibility to trade accuracy for reduced resilience overhead, thus better performance. Nowadays, GPGPUs are commonly deployed on supercomputers. In the first row of this slide, we show three pictures of top supercomputers in the United States. We see all of them deploy thousands of GPUs to boost their performance. And in the second row, it shows a picture of Titan supercomputer. Titan is the first GPU-based supercomputer to perform over 10 petaflops. It ranked the first place at the year of launch, and it continued to rank top 10 until it was finally replaced by Summit. While we enjoy the performance boost given by GPGPUs, we should also pay attention to their resilience concerns. There are thousands of GPUs deployed on the supercomputer. Therefore, failures are routine events rather than rare events. GPGPUs are prone to soft errors. The cause is high-energy radioactive particles, such as cosmic rays. They will cause bit flips in memory cells. Those soft errors are random and not permanent, thus are harder to detect. As contrast, hot errors are easier to detect because they are permanent. The impact of soft errors can be masked output if they occur on non-critical paths. And the other cases are silent data corruption, hangs, and crashes. Silent data corruptions are the hardest to detect because in this impact, the application will execute successfully, but the output is corrupted. So we have to use extra methodology to detect this impact. Therefore, this is the focus of this paper. In terms of protection strategies, we list the two strategies here. The first one is this recomputation model. Basically, we execute one instruction twice. It can either be executed in parallel using double physical resources or execute in sequential. That will take double time. Another commonly used strategy is error correcting code. For example, on single bit error correcting, double bit error detecting. So what's the overhead of this strategy? Let's take Titan supercomputer as example. In this table, it shows the cost of error correcting code on Titan. We see that with ECC turned on, it will consume a lot of bandwidth and available memory. And if we look from the system perspective, it will consume a total of 14 gigabytes. This fact shows that error protection is expensive. Therefore, we already observed that some researchers opt to turn off error protection for better performance. Therefore, in this paper, we want to strike the balance between reliability and overhead. Basically, we want to offer a more flexible middle point that can provide acceptable resilience requirement with reduced overhead. Towards this goal, we propose this accuracy-aware resilience. We found that not all silent data corruptions are unacceptable. Let's take a look at this code snippet. It is a code copied from Black-Scholes benchmark. It defines this L1 norm as evaluation metric. If this value is greater than a threshold, the test will fail. Otherwise, the test will pass. So basically, if the output is correct, if it is max output, it will pass. And more importantly, even though the output is corrupted, but if it is within an acceptable range, the test will also pass. Therefore, we split silent data corruption into two categories. One is SDC accept, another is SDC reject. So we define the accuracy-aware resilience as this. If a user can tolerate a quantifiable loss in the output quality, the resilience overhead can be reduced or even avoided. In this paper, we take a hierarchical approach. In terms of fault injection, characterization, and use case, we follow the GPGPU application resource allocation hierarchy, starting from kernel level to city level and to warp level. And we launch experiments on 15 benchmarks. On average, we launch 10K runs per benchmark kernel. We classify fault injection outcomes into 5 categories: masked, SDC accept, SDC reject, detectable data corruption such as easy detectable negative values or null values, and all other outcomes like hangs or crashes. The first 2 are benign outcomes, and the rest 3 are non-benign. In terms of evaluation metric and threshold, we consider they are provided by users, and in fact, we are able to find the definition of such metric and threshold in most of the benchmarks. In terms of fault injection strategy, we use our previous published dynamic instruction count-based fault injection solution. Here we use dynamic instruction count as the resilience proxy because GPGPU applications take the simple instruction multiple execution philosophy. Thus, if 2 threads share the same DI count, they are likely to execute the same set of instructions. Thus, they will share the same resilience behavior. The fault model we use here is single fault injection model. We use GPGPU SIM as the simulator. As shown in these figures, we group the CTAs or warps into several groups based on their distribution of thread dynamic instruction counts. And in each group, we pick one thread as a representative, and we perform fault injections on those selected threads. If you are interested in this approach, please refer to our Micro 2018 publication. In terms of characterization result and overhead reduction methodology, we start from the kernel level. This stacked bar plot shows the error distribution of Black-Scholes benchmark. We see that if we only accept masked output, the percentage of benign outputs is only 31.8. Here we define the percentage of benign outputs as resilience coverage, which is very low. But if we are able to tolerate some loss by accepting this SDC accept output, the resilience coverage is increased to 89%. This value can be acceptable for some user. Say if we define the acceptable resilience coverage threshold as 85%, then we are satisfied with this resilience requirement. Therefore, if we only accept perfect output quality, we cannot tolerate any overhead reduction. Thus, we have to deploy the full recomputation model. But if we are able to accept this SDC accept, we are able to have this 100% overhead reduction. At CTA level, we can provide more flexible choices. This figure shows the error distribution for hotspot. We see that if we only accept perfect output quality, the resilience coverage is 66.2%. Even if we accept SDC accept, the resilience coverage increased to only 83.8%. None of them passed our predefined threshold, which is 85%. Therefore, we take a deep look into the CT level. We see that the threads are now grouped into two categories. On group 1, the threads are very error resilient. Thus, we can relax the protection for threads in group 1, and we only need to protect threads in group 2. Therefore, at CTE level, if we are able to accept default output quality, we are able to give the choice of resilience coverage at 99.6% with an overhead reduction of 26%. Similarly here, at warp level, we can give user more flexible choices. This picture shows the error distribution of word count kernel on kernel 5. This kernel is a very error resilient kernel. We see that the resilience coverage is 88 to 89% at kernel level, and some users can satisfy this resilience coverage and accept overhead reduction of 100%. If we take deeper into the warp level, we see that the threads are grouped into two categories, and in group 1, the threads in this group are even more error resilient. Thus, we are more confident to relax the error protection. Therefore, at warp level, we are able to provide a resilience coverage of 96.6% still with an overhead reduction of 75%. Basically, with the choice of different level, with the choice of different output qualities, we are able to provide users 3 solutions here, which has different resilience coverage and overhead reduction. So users can choose the solution that works best for them based on their requirement. Conclusion. In this paper, we want to resolve the question, can we provide lightweight but still reliable GPU computing? Basically, we want to strike the balance between the reliability and overhead. Towards this goal, we propose this accuracy-aware resilience. If a user can tolerate a quantifiable loss in the output quality, one can reduce or even totally avoid the resilience overhead. Our solution can be best summarized using this table. Basically, one can first choose their acceptable output quality, which is only masked output is acceptable, or we can tolerate some loss in the accuracy by accepting this SDC accept. So with the output quality chosen at different levels, which are kernel level, CTA level, and warp level, we provide different choices that vary the resilience coverage and overhead reduction. So basically, users can choose the solution that works best for their choices. In this way, we are able to strike the balance here. Thank you for listening.